Right. We continue with part 2 of our course outline, which is Boolean algebra. But before we begin with that, sign bit, sign bit, magnitude, representation. Right. A few people from the computer engineering department noted 0. This is how I defined the sign bit representation. Which is not correct. I wanted to justify that error, but I just realized even the examples I gave, they contradicted this example. Because the examples I gave, they were 12 base 10, which is 000 1100 base 2. This 0 means it's positive. 1 negative. So for sign bit representation, negative 12, 1, 1 is negative, 0 is positive. I just made the error at this stage. Right, so if you can verify that, thank you very much, computer engineering department. It means people are actually reading. People are actually reading. We thank God for that. Now, we have that out of the way. We move on to Boolean algebra. What is Boolean algebra? After we are done with the number systems, how do we represent digital signals? After we are done with the number systems, that is how we represent the number systems, how we represent digital signals. We now move on to the Boolean algebra systems, which is basically a mathematical logic consisting of variables and operators. So Boolean algebra, what is it? A lot of definitions. I'll give, I think, 2 or 3. So mathematical logic consisting of variables and operators. By variable, we mean our states 0 and 1. And by operator, these are the gates which we are going to define: the AND, the OR, the XOR, the NOT, the OR, the gates. We are going to define the operators later on. So this is a way to express logic functions algebraically. A way to express logic functions algebraically. Or another definition, a set of rules used to simplify given logic expressions without changing its functionality. I think this one is important to note. Rules, mathematical rules used to simplify logic expressions. Hold on to the definitions. They'll probably become more clearer when we start to deal with the logic expressions. Just a minute from now. All right. Now, what is the approach when you want to build up a circuit? Hold on to the definition of Boolean algebra. We'll deal with it later on. What is the approach when you want to design a circuit? When you want to build up a circuit? When you want to build up a circuit, you have a problem which requires a circuit. I'll give an example of a problem later on. You have a problem which requires a circuit. In the circuit is obviously the solution. What you do first, before you build up your circuit, you analyze the problem. Now at this stage, you determine the inputs of your system or the circuit, the inputs of your system and the outputs of your system. So you have a problem and you need a solution. The solution is the circuit. Before you construct your circuit, you analyze the problem. Analyzing the problem is knowing what are the inputs of your logic circuit. The inputs can be the variables we just defined when we defined the Boolean algebra. The inputs can be zeros, can be ones, variables. So with the combination you have of zeros and ones, what is the output? What is the output to solve your problem? That is the analysis. What is the output to solve your problem? Step number 2, you then go to the design part. Now, given a task to develop a circuit that accomplishes that task, there are bound to be many possible implementations. If you have a problem and you have 10 people in the room, they probably have 10 solutions. If you have a problem and you have 10 people in the room, they probably have 10 solutions. But the design part for us in the logic design and switching circuits is to decide which of those 10 solutions is the best of the solutions. In our case, which of those 10 circuits to our problem is the best. The design part decides which circuit is the best. And all this is based on size of the circuit, based on size of the circuit, based on the power, based on the performance of the circuit. So when we talk of a circuit, I'll give an example. When we talk of a circuit, this is what we talk of. We have a television. We have a television problem. We have a television, 2 switches. We have a TV, that operates with 2 switches. Switch 1 and switch 2. Right. The problem is when switch 1 is on and switch 2 is off, then the TV is off. Switch 1, switch 2, TV. What we are doing now is analyzing, the analysis part. We have a TV. Switch can either be on or off. Two switches. When you have two variables, when you have two variables, the number of possible outcomes, outputs, is 2 to the power of n. Take note of this. From the analysis of our problem, when we have two inputs, this means outputs 2 to the power of n. When we have n inputs, sorry, when we have n inputs, n variables, then our output is 2 to the power of n. Very important thing to note. So in this example, we had two inputs. It means our outputs were supposed to be 4 of them. Right. Going to our example, we have two inputs, switch 1 and switch 2. Possible outputs, they are supposed to be 4. Right. When the switch S1 is off, and when the switch S2 is off, our TV is off. When the switch S1 is off and the switch S2 is on, our TV is off. The same here, when S1 is on and the other one is off, our switch is off. Our TV is off. Only when both the switches are on is our TV on. I can build a circuit which will function. I can build up a circuit which will function to give these outputs provided these inputs S1 and S2. I can design a circuit to give these outputs provided the inputs S1 and 2 have just been given. I know this circuit, what it looks like. This is an AND gate. It is like this: S1, S2, our TV. This whole part here, we just did here, can be summarized by this circuit. I'll later on define the operators which we'll be using later on. I was just trying to give an example of a problem we had, and we wanted to produce a circuit which only gives a result which is the TV on provided S1 and S2. Right. Boolean algebra definition, mathematical logic consisting of set of elements, variables, zeros and one, which can be simplified, which is used to simplify circuits, I need you to take note of one, variables from the definition of Boolean algebra. I need to take note of variables, 0, 1, inputs, outputs, n to the power of n. I need to take off net of operators and or. We have XOR, we have NOR, and all that other stuff. But these are the basics. Right. Before we get to our operators, there are rules and laws of Boolean algebra. Chat. Say, can you please repeat the definition? Definition. I put out three definitions. One, mathematical logic consisting of elements which are the variables and operators. Mathematical logic consisting of set of elements, variables, and operators. Boolean algebra definition, a way to express logic functions algebraically. Boolean algebra definition 3, a set of rules used to simplify logic expression. You cannot define Boolean algebra using only one definition because there are a lot of things to consider here. The first definition I gave you only considers variables and operators. I think the other one considered simplification. Simplification of Boolean functions. From the definition of Boolean algebra, this is what I would like for you to understand. Right. We move on to some of the rules which are used in Boolean algebra. Some of the rules which are used. We have rules and laws for Boolean algebra. We have what we call the commutative law. Commutative law. These laws will help you when you are simplifying a circuit. You need to understand at the beginning, claim them. Later on, understand them. Once you understand them, I think there'll be no need to claim. We have A plus B is the same as B plus A. We also have AB is equals to BA. All right, I think I need to introduce our operators before I introduce the laws. Let me introduce our operators because I think we need that knowledge when we define the laws. Our operators, we have the OR. Well, let me do this. Let me put up a table. Let me put up a table with two variables, A and B. We have operators OR. Okay. And we have not. Right. So we have our operators. One, two, three, four. Right. Notice the way I'm putting in the variables. If you have two variables, A and B, inputs, two inputs, I mean, A and B, it means our output will be 2 to the power of n. 4 outputs. If you have two inputs, then we have 1, 2, 3, 4 outputs. Right. How do you put out the outputs? Yeah. The simple way is to do this. If you have 4 outputs, right, you go 0, 1, 0, 1. If you have 8 outputs, you go 0, 1, 0, 1, 0, 1, 0, 1 until you have 8 outputs. If you have 16, the last, this one, the last, so if I have 4, I have A, B, C, D. The last one, our D, last input, it goes 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 until you reach 16 variables. The second one, it goes 0, 0, 1, 1, 0, 0, 1, 1. Third one, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. It continues like that. The last one is 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. You continue like that. So if I only have 4 variables, how do I, if I have 4 outputs, how do I input the variables? So it's 0, 1, 0, 1 for the first one. When it comes to the second one, it's 0, 0, 1, 1. This will be useful when you are asked to prepare what we call truth tables. Definition, truth table. Definition, truth table. Do we have a definition, a truth table here? I think we might need it. Truth table. Definition. The truth table completely specifies outputs. A table that completely specifies all the outputs for given input combinations. Table that specifies outputs for given input combinations. So our input combinations, we have A and B. And our outputs, we have OR and let's put a third one, which is not. Going to the design part, AND gate. What does it look like? OR, we start with OR. If I have 2 inputs, OR gate looks like this, which with 1 output. Our output is OR. 2 inputs. Possible combinations 0, 0. A can be 0, B can be 0. A can be 0, B can be 1, 1, 0, 1, 1. These are the input combinations. What will be the outputs? If I have an OR gate, it works as a plus. OR gate works as a sum of A and B. A plus B. So the output here is 0 plus 0, which is 0. Here is 0 plus 1, which is 1, which is 1. 1 plus 1, it's not 2, it's 1. This is the OR operator. This is the OR gate. This is how you represent it in a circuit. Representation in a circuit. We have the AND gate, 2 inputs, output, and A and B. This one works as a product. So if you have 2 inputs, A and B, the product is the output. So here our 2 inputs, A and B. What are the possible outputs resulting from the combinations of A and B? The first one is 0 times 0. The first one, 0 times 0, it's 0. Then we have 0, another 0, and a 1. 0, 0, 0, and a 1. 0 times 0 here, 0 times 1, 1 times 0, 1 times 1 is 1. Then we have the NOT, which is basically the opposite of any input. I think the NOT doesn't fit here well. Let me do this, which is the NOT. If you have an input A, output NOT. If your input is 0, the output will be 1. Basically the opposite. If you have an input 1, The output of a NOT gate is 0. I think the NOT gate looks like this. A input, output is NOT. I've defined 3 gates for you. I've defined 3 operators for you. The OR, the AND, the NOT, and their respective gates. I'll now go on to explain the rules because I only need these 3 to explain the rules. The rules which we are going to be using, right. Commutative law. A plus B is equals to B plus A. You can prove this using your truth tables. If I have 2 operators A, B, what is A plus B? What is B plus A? So if I have 2 inputs, 0, 1, 0, 1, 0, 0, 1, 1. What is A plus B? Here is 0, here is 1, 1, 1. What is B plus A? 0, 1, 1, 1. It sounds simple like this. A plus B is equals to B plus A. It sounds simple, but when you are given a very big circuit that needs simplification, you probably won't identify where the A plus B's and the B plus A are. So you need to understand and know when to identify this law, commutative law. The same with AB and BA. What is AB? AB is A times B. So it's 0 here, 0 here, 0 here, 1. B times A, the same. Commutative law, done. You will be using these laws in simplification of circuits. If you have time, you can prove them using truth tables. This is the truth table. Right. The rest of the laws, we have, let me share my screen. You can Google them as well. You probably find mistakes, which is a good thing. Let me share, where is it? Let me share. Okay, just a minute. I need to share some of the laws. I don't want to write them here. Okay. Some of them we have De Morgan's. I think this is the biggest of them all. I'll need to explain this one. We have absorptive law. Just a minute. Where are we in Africa? Logic design. Right. Rules and laws. This one. Right. I want to share 10 minutes. I want to share the screen. Okay, let me just share the whole screen. Right. Are you able to see the photo I've just shared? Right. Here we are. Are you able to see that photo?
Yes.
Just a minute. All right. You can see my screen, right? All right.
Yes, sir.
We have highlight pen. We have the first one I introduced, this one. Commutative law, A plus B is equals to B plus A. Simple. You just need to claim these laws at the beginning. Later on, you will understand them because there will be need to understand them. We have the associative law. Take it as it is. If you want to prove it, then you can as well use chat. You can as well use the truth table. Can we see an example of a larger commutative circuit if it's okay? Yes, you probably see it, but not now. We are going to take this small. For now, deal with A plus B. When I give you a very huge circuit, you'll be using these laws to simplify that circuit. You can have a circuit with uh, 10 or more operators. But using these laws, you can reduce it to only 2 operators. That is why we have these laws. I'm saying you can have a circuit like A, B, C plus A naught, B naught, C naught plus AB plus A plus C plus AB naught plus goes on like this. Many operators. We have an AND operator here. We have an OR operator here, a plus. We have a NOT operator here. We have another NOT. We have another NOT. Many operators. This whole circuit can be simplified maybe to only A, B. How do you simplify it to only 2 operators, A and B? How do you simplify it? You use these laws. We'll get on to the simplifying part, but I just wanted you to get an understanding why we have these laws. These laws are used to simplify logic circuits. When I gave the definition, I talked of analysis in design. In the design part, I gave an example. You can have one problem and 10 solutions. This is one of the solutions here. This is one of the solutions here. But in terms of size, in terms of performance, is it okay to use this solution if we can as well use a solution like this? How we go from a solution like this one, which is correct, but in terms of size, you have used like 10 or more logic gates instead of using only one logic gate. In terms of performance, the more logic gates you have, probably the less performance. You need a better solution. Design part provides you this. How do you get here? You simplify. How do you simplify? You have these laws. So these are the laws we have. If you Google, you get this picture, or you get it from here. So we have commutative law, associative law, distributive law, then we have the absorption law. In this picture, it also has solutions like how did we get there? Here, it has a solution. How did we get there? From A, in this example, we had, this is the absorption law. We had A, let me write it. Let me write it on my own, 5 minutes. Okay, absorptive law. If there is a way, if you don't even know the laws, but you know how to manipulate algebraic functions, you can get from this point here to only this point. If you don't know the laws, you didn't claim the laws, but you understand how to manipulate them, you can get from this point to this point. If you are the kind of guy who claims understand the law too, if you are the kind of guy who is able to manipulate, understand this solution. So for example, A bracket A plus B. This is the same as A plus A, B. I've just simplified what is in the bracket. A times A plus A times B. This is what they are doing here. Now, what is AA? What is AA? If I have 2 inputs, A and A, if I provide a truth table for that, 0, 0, 1, 1. What is AA? AA, 0 times 0 here, 0, 0 times 1 here, 0, 1 times 0, 0. Then we have 1 times 1, 1. What is AA? AA is the same as A. Is this true? A is 0. Forgive me here. Let me see. We have only one input here. One input. I want to prove AA is equals to A using the truth table. We have only one put. AA is equals to A. Proof. We have one input. A is equals to 0, 1. A times A is equals to 0, 1. Because 0 times 0 is 0, 1 times 1 is 1. Which means A times A is the same as A. If you understand how to manipulate what I just did there, I know how to manipulate the numbers. I don't know the laws, but I know how to manipulate them. So it gets me to a point where I understand that AA can be the same as A. So if I am to simplify from this point, I know that this is equals to A plus this remains the same, AB. If I can put out a bracket, this is 1 plus B. But what is 1 plus B? If I don't know the laws, but I know manipulation, I can find 1 plus B is equal to 1 plus B is equal to 1. Do we have time here? Let me prove what is 1 plus B. Let me prove what is 1 plus B. I think the video is ending. I think we've reached 1 minute, 20 seconds. I think I can be able to. 1 plus B. If you understand manipulation, what is 1 plus B? If I have B, 0, 1. What is 1 plus B? 1 plus 0, 1. 1 plus 1, 1. So 1 plus B, whatever the case, it is equal to 1. So this is the same as A, 1. Now what is 1 times A? 1 times A is equals to A. So this whole law number 2, you can either claim it results to A, or you can either learn how to manipulate the numbers using truth tables. With practice, you know how to manipulate the variables and all that other stuff. In the exam, you won't have problems. If you forget what are the laws, you can always get the answers through manipulation of the variables. Let us continue. Let us continue. I'm ending this session because it probably end on its own. Let us continue with other laws. The most important of